In this project, we developed a smart signage system for marinas to be used to guide tourists to reaching their docking spots. During summer, marinas are full of tourists who want to dock their boats for the night. In most of the cases, it's the first time they visit the marina, and so they don't know where to dock. What happens usually is that the tourist has to get off the boat and ask to a marina worker where to dock. Then, in the crowded and unknown marina, the tourist has to reach his docking spot. To solve this problem, we propose a smart signage system that automatically generates signage for the tourist that has to reach their docking spot. When a boat enters in the marina, it's automatically identified with a camera that reads the license plate or by using the GPS of the user's device. Then the system assigns a free docking spot and communicates the decision to a set of displays. Each display will show a custom message to guide the user in the marina. Once the docking spot is reached, a special click communicates to the system that the docking operation is completed and the signage is removed. We start with an overview of the components. We have a dock device in each docking spot, some monitor devices to show signage, a camera device at the entrance, a LoRaWAN gateway to talk with all the devices, a marina server to connect the system to the cloud, so the cloud system with all the computations, and a web interface. The network architecture can be seen here. We have the dock devices and the monitor connected with LoRaWAN to the LoRa gateway, while the camera are directly connected to the cloud using MQTT. The LoRaWAN gateway converts the messages in MQTT to communicate with the cloud system. A web interface can be used to make reservations and tracking the GPS. The first device that we want to explain is the camera device. We used a Raspberry Pi 4 board equipped with a USB webcam. The network interface used is Ethernet. On the camera device runs a text recognition algorithm to detect boat license plates. When a boat is detected, an MQTT message is sent to the cloud. The dock device is equipped with an LED and a button, which is inside a special clit that we developed. The network interface used is LoRaWAN and Ethos for testing. The clit sensor is 3D printed in PLA and is made of 3 pieces. When a rope is tightened on the clit, the button is pressed, and so we can detect when a boat is present. There is also the option to have multiple docking spots handled by the same board. The LED is switched on when a boat has to dock and is turned off when the docking operation is completed. The message exchange is done with LoRaWAN. By listening to the LoRaWAN messages, the board will know when the docking spot is assigned. Every time the docking spot changes status, a message is sent. The monitor device is equipped with a display and listens for the assignation of docking spots. The images and the text that has to be shown are computed inside the board locally. In our prototype, the display is controlled with an E2C bus. The network interface used is LoRa also in this case, and Ethos only for testings. On the display are shown the boat license plate and the direction to follow. If more boats has to be served together, the screen changes the content continuously.
The cloud system architecture is composed by 3 main parts. The first part, the AWS cloud part, is composed by a DynamoDB in which reservation and docking spot status are stored, 4 Lambda function, and a IoT core broker. The Lambda function gets reservation is used to make a reservation by the web page. The Lambda function GPS handle is used to process the GPS position got by the web page when the user enter in the marina. While the Lambda function assign dock is used to assign a free dock when a boat enter in the marina and to generate the signage on the monitor. And finally, the Lambda function remove reservation is used to remove the reservation when the docking operation is completed, and to update the docking spot status when a boat leaves the dock. While in the marina, the monitor and dock devices are connected to a LoRa gateway via LoRaWAN, and the LoRa gateway exchanges messages to the IoT core broker through an MQTT bridge, while the camera devices are connected directly to the IoT core broker. The web page is hosted on the GitHub pages. Evaluation of the plate recognition system. On a sample of 20 images, only 35% are detected correctly. The main problem is dealing with pictures taken by an angle, for example like this picture, while in this picture, when the camera is perpendicular to the test, the algorithm detects well the plate. But in the real implementation, the camera position is well chosen in a position when the probability that the camera is perpendicular to the text is higher, so the algorithm will perform well. The response time, so the time from when the picture is taken to when the message is received by the IoT core broker, is about 2 seconds. Evaluation of the dock device. On 10 times of the off procedure, we got only 2 false negative and 0 false positive, and we consider this an acceptable result, considering that the CLIT model is a very basic prototype. Using this LED light, which is the light used in the traffic light, the power consumption is about 0.47 watt-hours per day. And if the customer prefers to power the dock devices with batteries, it is possible, because with this low power consumption, with a Lion pack of 6000 mAh, a single dock device can be powered for about 6 months. Evaluation of the monitor devices. In the final product, we'll use the monitor that are used in the routes to get an higher visibility also in the sunny days. For example, like the monitor in the picture. This specific monitor has a power consumption up to 2700 watt. It depends on how many pixels are turned on, so it must be powered by the marina power line. The response time, so the time between the boat detection and the signal visualization, is around 4 seconds. Usually, the speed limit at the entrance of the marina is about 3 knots. So, with this speed, the boat can travel for at most 6 meters. So, the first monitor must be placed at least at 6 meters from the camera, and in this way we are sure that when the boat reaches the monitor has a useful information. When we use the GPS, since we have a GPS error of about 5 meters, a reasonable threshold distance must be at least 11 meters. The future works. Now there are some problems between IoT Lab and the Things Network, so the evaluation of the LoRaWAN are estimated and not real. So we will like to see a comparison between our estimated and the real performances. Another improvements that we will like to see in our project are a plate recognition system with a higher precision, a login system to make reservation and to use the GPS service, and give the option to use only the GPS service if a boat doesn't have a license plate, for example the small boats.